Video will explore the relationship between a planet's orbital velocity, and thus its period, and its distance from the Sun in our solar system. It will make use of a hyperbolic funnel and steel balls to play the role of planets. Note that the curvature of the funnel surface is a proxy for gravity. You can picture the Sun as the hole and observe that the curvature increases as you get closer to the hole, just as gravity increases as you get closer to the Sun. In this video, we will work exclusively with circular orbits, which have constant speed, but this is useful as all of the planets in our solar system have elliptical orbits that are close to being circular. Let's start by placing a ball in a circular orbit. We can crudely determine the period of the orbit using the time code on the video, and find it to be pretty close to 2 seconds. We now have two balls in orbit, one pretty much in the 2-second orbital period, shown earlier, and another in a smaller orbit. Let's explore our understanding of orbital motion with a pure instruction question. Two balls are placed in orbits. How will the orbital period for the ball in the smaller orbit compare to the orbital period of the ball in the larger orbit? Please record your vote on a piece of paper and explain your reasoning. Your instructor will now stop the video. We now cut to live video of the two balls in motion. You can see that the ball in the smaller orbit will have a smaller orbital period, although we need to watch for a while for that to be apparent, and see that the inner ball passes the outer ball. The ball in the smaller orbit also has the greater speed. It has to move faster to withstand the greater gravity closer to the Sun, and the greater surface slope of the funnel near the center. Here is an animation illustrating the orbital motion of the inner 6 planets in our solar system. Note that it is easy to see that orbital period increases with orbital size. If you look at any pair of adjacent planets, the inner planet will shortly pass the outer planet. This relationship is expressed as Kepler's third law. P squared equals a cubed. The orbital period squared is proportional to the semi-major axis cubed. But we can write it in terms of radius, as p squared proportional to r cubed, since we are working only with circular orbits. We can create a mini solar system using the funnel, and note that the balls with smaller orbits move more rapidly and have smaller periods. We can show why this is true starting with our expression of Kepler's third law for circular orbits, and realizing that the orbital path is just the circumference 2 pi r of a circle of that radius r. So the period is the time it takes to move through a circumference at velocity v. We can get rid of the constants 4 pi squared, since this is just a proportionality, and after a little bit of mathematical simplification, we can show that the velocity of an object in a circular orbit is proportional to 1 over the square root of the radius. So the smaller the orbit, the faster the planet, or steel ball, moves.